Hi everyone, welcome to today's class. So this is my topic number 16, and for topic number 16 I have chosen conductance from electrochemistry, and obviously it is a physical chemistry chapter. So we all know that CSIR NET is now started knocking at our door because not much time is left actually. We are going towards the date. So I thought that maybe I should cover some topics which are actually easy to understand, and questions are coming from this topic also. So that kind of topic I have to cover first. So that's why I have started electrochemistry part also, and the conductance in electrochemistry is very important. The theory kind of questions are also coming from this chapter, and also the mathematical problems. So both are important. So you have to have idea about the conductance in a clear way, so that the theory based question also you can attempt. Okay. So let's start with today's topic. So first, the what is the conductance? So we actually in 10th standard, I guess. So we have read about the Ohm's law, right? V equal to IR. In physics also we have read this, right? So V equal to IR is a common formula, and also very important. So I is here current, R is the resistance, and V is the voltage. Okay. So here from when we were reading this, we have also studied the what is the resistance, right? So this is rho L by A. So where rho is the resistivity, R is obviously resistance, and L and L by A is the cell constant. Okay, this is not written here, but L by A is a cell constant, means it is a constant value for a particular cell. Okay, so for cell we know that. So you have to have idea about what cell is. So cell is like battery is a kind of cell. So in the cell there is cathode portion, and there is anode portion, right? So the current flow is going on there. Okay, so one will be cathode, another one will be anode, and oxidation, reduction reactions are going on inside the cell, and so that we get the current flow, electron flow, and also the current flow, right? So L is the distance between these two cells, and A is their area. Okay, so this is the thing. So from that only we can express the resistance of a particular cell, of a cell. Okay, so what is resistance actually? It is the hindrance which affects the passing of electric current. Resistance, so we know, right? Bacteria resistance, these things are these words actually we are familiar with. This bacteria is resistant with one antibiotic. That means it has the power to withstand that antibiotic capsule or medicine, right? So it is the hindrance which, for current we are reading right now. So it is the hindrance which affects the passing of electric current, which is proportional to the L. Let's say forget about the cell. So we know current flows in, with the by the wire, right? Through the wire actually. So current flows actually. So if the length of the wire is L and its area inside the wire, the area is A. So it is inversely proportional to area, and it is proportional to the length of that wire. Okay, and rho is a constant value, so resistivity it is. So we will talk about it, but it is not important here actually. Okay, so now we are reading what conductance. So we why we are now we read the Ohm's law and the resistance. Why? Because conductance is the ability of a material to conduct electricity. So How can we relate this to? The conductance is actually the opposite of resistance. Resistance means the hindrance which affect the passing of electric current, whereas the conductance is the ability of a material to conduct electricity. It helps uh, in the passing of current, and it actually hindered that, right? So it is actually the conductance, it is denoted by lambda. It is actually inversely proportional to 1 by r. Okay, not proportional, it is equal to 1 by r. Okay, so this lambda equal to 1 by r means this equation we have inverted, right? So what we got actually, 1 by p, we have separated it, and E by L. Okay, so this is a important formula, this one. So that's why we have read this, how this resistance actually depends on these factors, and from there we have got the formula for conductance. Okay, so 1 by rho into A by L. Fine. And L by A, I have talked that cell constant. Okay, whenever in a question that cell constant value is given, that it means that L by A, and L is the length, right? So what will be the unit of L by A? Will be, let's say L is in semi. Okay, so it will be semi, and if A is semi square, so the unit of cell constant will be semi inverse. Okay, now the conductance. Okay, rho is here resistivity. Okay, fine. Now conductance, we got this formula, right? So again, why we are reading it? Because we want to uh, convert it to another expression, important expression of conductance, that is the this one, lambda is equal to kappa into A by A, or sometimes let's say K is also used, or kappa. Okay, A by L. So 1 by rho is equal to kappa. So K is 1 by rho. And what it calls? We call actually rho as resistivity. So the kappa is the conductivity. For resistance it is resistivity, and for conductance it is conductivity, right? Or specific conductance. Fine. Now K is this. Okay. So how can we now define K? To see, when L is 1 unit, let's say 1 semi, and A is 1 semi square. Okay. That time what we get? We get lambda equal to kappa. That means when for a cell we are reading, right? It is from electrochemistry only we are reading. So for a cell, let's say for 1 semi cube of electrolytic solution, let's say, the conductance will be the kappa. So we can define the kappa like that. That it is the conductance of 1 semi cube solution, electrolytic solution, which we took actually in the inside the cell. Fine. So we can define kappa with conductance. Fine. Now the unit. This is most important thing in this chapter. You have to have a clear idea about what is the unit of conductance, resistance, resistivity, conductivity, specific conductance, same thing. And we will talk about also molar conductivity. Okay, molar conductance, equivalent conductance. So these all unit you have to understand. Okay. So first we know resistance. Unit of resistance is ohm. Okay. And so also ohm. Okay. So unit of conductance now. Unit of conductance, we know that conductance is 1 by R. So obviously it will be 1 by ohm. So ohm inverse. Fine. In SI unit, the unit of conductance is the Siemens. Okay, it is sometimes written as S. Okay, ohm inverse or Siemens. Fine. Unit of conductance we know. Now what? Unit of conductivity. Conductivity means or specific conductance, that is kappa. What will be it? So we know now lambda is ohm inverse. Fine. Let's say it is CDS. Okay. Lambda is ohm inverse. A, which is the area, is semi square. Fine. L is semi. Fine. Now K is, we know, ohm inverse semi by semi square. Correct? By semi square, correct? So it will be ohm inverse semi inverse. Right? And let's say another thing, let's say in SI unit, it is Siemens meter square and meter. It will be Siemens meter inverse. Okay, simple. So in this slide, we have read the unit of conductance and also the conductivity. Okay. Now the molar and equivalent conductance. Okay, this is very important. So we know conductance is this. Okay. So molar conductance is conductance of 1 mole of electrolyte. Okay. When we took particularly 1 mole of electrolyte from the electrolytic solution, the conductance shown by that is the molar conductance. How can we represent that? It is denoted by lambda m. Fine. But how can we got that? Okay. So let's take this one. Okay. So let's say, okay. So lambda equal to kappa into A. I am multiplying the both upside and downside with A. Okay. So this will be there. Now we know it is now V. Okay. So this is the volume of the electrolytic solution with you, right? So it is the V and this is L square. Okay. And let's say now L is equal to 1. Let's say L is 1 semi or 1 unit. Now what will be the equation? This one. And now if we take, this is just a version of the expression of the conductance. And we have taken L equal to 1. Fine. Now what we can say, we have to know about molar conductance, right? So we have to, for 1 mole we have to know the value of conductance. So say let's say we have taken n mole. Okay. So for n mole, this is the n mole, this is the expression. So for 1 mole, what will be the expression? Lambda by n equal to K into V by N, right? N is the number of mole. This can be expressed by lambda m into kappa into Vm. Vm is molar volume. V is the only volume of the electrolytic solution. And now we got the important equation for molar conductance, that is kappa into Vm. Please remember Vm is the molar volume. Okay. Vm is V by N. Fine. And now, okay, we have to convert it in another expression. Fine. So we know Vm. Fine. Now let's say different thing. Concentration. What is the concentration? We know mole by volume, right? Mole per liter. We have we have we use the unit of concentration as a mole per liter. Okay, most of the time, right? Or molarity, normality. For any case, okay. So this will be the mole per. These all are mole per volume units. Okay, for concentration. So now here only one mole, right? So n equal to 1. Now what will be the C? C will be, now here only if I put 1 and now V will be Vm, because I have taken this for 1 mole. So for 1 mole volume is molar volume, right? Vm. So C will be 1 by Vm. Fine. Now Vm will be 1 by C, obviously, from this. Now we get another important expression of molar conductance. That is what? That is this one. Okay. So this one is also one important formula. Okay. We have highlighted it also. So these two you have to remember. One is kappa into molar volume, and from the molar volume, when we consider the concentration term, we saw that the concentration is actually equal to 1 by Vm. And we put the value, we got this expression also. Kappa by Cm. Okay, means molar concentration. Fine. Now the unit of molar conductance. I previously told you that units of these all terms are very important here. Okay. So for the units, lambda m equal to k into Vm. We know that. This also we know. So unit of molar conductance we have to see. So now we know kappa is ohm inverse, semi inverse, and Vm is molar volume, volume by mole. So semi-cube, let's say, is the volume and mole inverse, right? And if we put these two, the unit will be the ohm inverse semi square mole inverse. Fine. And another way we can write Siemens meter square mole inverse, right? So if you can remember these units, that will be very much helpful. And but if you not, or you are confused in the exam hall that what is the unit of this, just remember these formulas, these two, and you know molar volume, and if you know kappa. If you also forget the kappa or confused about that, we know that lambda is equal to kappa into A by L. This is simple, right? And this is obviously we know ohm inverse, and A by L also, this is easy. This is semi, right? This unit of A by L is semi. So you can get easily the kappa unit, and you can put kappa, unit of kappa here, and we can get the unit of lambda. Okay, I am telling this because I am considering that if you forget about that the unit. Okay, sometimes I also forget the unit, so I am actually calculating in my mind, or if I have a pen and paper or copy is given in the exam, obviously you know. So I just in the rough page I just write this expression and I can find it out, right? Now next. So equivalent conductance. Molar is there, so equivalent will be there. So equivalent conductance is the conductance produced by the dissociation of 1 gram equivalent of electrolyte. So which was 1 mole electrolyte for molar conductance? The same thing, this is for 1 gram equivalent of electrolyte. Fine. It is denoted by, no, this is wrong, equivalent. Okay, and this is again the same thing, right? Just we have taken Instead of mole, we have taken gram equivalent. Fine. This will be kappa by CEQ. This is the concentration in equivalent. Equivalent concentration. Okay. And for 1 liter solution, C equivalent is expressed as normality. So obviously we know, we have read in class I think 12 or 11 solution chapter. So we have actually the conversion of molarity to normality, everything we have read about. So normality is, what is normality? Normality is the number of gram equivalents of solute per liter of solution. Okay. So in most of the cases, this concentration in equivalent is actually expressed in normally. In the questions you can see. So you have to have idea about normality and molarity here. Okay. So normality is the number of gram equivalents. How we can write that? Let's say this is the normality. We know for any concentration, generally concentration is moles per liter, right? So per liter is there. And for the equivalence, it is gram equivalent per liter. So per liter is there obviously, but how can we write? Okay, let's first just write equivalence. Okay, but what will be the equivalent actually? We know moles. What is actually moles? When we talk about moles, moles can be expressed in various way. But if we take like the weights, okay, so it will be the given weight or taken weight by the molecular weight or molar weight, right? So this will be, let's say, x by a. Okay, but here the same thing, the taken weight x, which is taken actually for electrolyte, we have taken that solution na. So this is the weight of that, and by equivalent weight of that solute of that electrolyte. Okay, so here it was the molar mass only, and here it is equivalent mass. Fine, and obviously Dieter, this is actually the x e into volume in liter. V actually volume in liter. Fine, and this is actually per liter solution. Okay, per liter solution. Yes, and if this is ml, then we have to actually multiply it with 1000. Clear now this is? And how can we actually write the equivalent weight? Equivalent weight will be, let's say, molar mass by Z factor. Okay, molar mass by Z factor. So we will understand that what is the Z factor in the next slide. And you know, obviously, we have read it in the class 11th, I guess. Okay, so if you forget about this, don't worry, I will make you understand this also. So equivalent, so here normality, for normality you have the all idea here. So equivalent weight per liter, and this is equivalence, and this is the equivalence can be written as the taken weight by equivalent weight, and we have the equivalent weight and molar mass or molar weight, that relation. Okay, so if you put the value also here, this will be what? This will be x into Z factor and E into V. Simple. Okay. So let's just come to the next slide. Okay, this I will come to later slide. The relation. Okay, first I will talk about this. What I have written here, the formulas which we actually just now we have read. Okay, this is the formula for molar conductance. This is for equivalent conductance. The title will be, how can we solve the question? How can we solve the question? Fine. So let's say sometimes you have actually seen that in the expression of lambda m or lambda equivalent, there is the expression is like 1000 into kappa by concentration. Right? But I have told you that this is the expression or this is the formula. So which one is correct? So I will tell you that both are correct. But it depends on what? It depends on the unit of that concentration and kappa. Mainly the concentration. Okay? So both units actually how much it matters. See, many of you just when I wrote this, many of you has questioned that we have read like this formula was like this, but why ma'am actually wrote this like this way? Because see, I can convert it to this. Okay, let's say for example the let's say kappa is in, what is the unit of kappa? Ohm inverse, semi inverse, right? Okay, it is like let's say x, ohm inverse, semi inverse, and for concentration it is given in molarity. 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 Now we have read about normality, but what is molarity now? This is it is the concentration of this one. This is actually the number of moles. We know that concentration is mole per liter generally. Number of moles per liter. Okay. So this is fine. Okay. So let's say this is given like this way. Molarity. Okay. And Y concentration is Y molar. Y molar. Like this you have given. Now if we put the value lambda m is equal to let's say x by y. Is it correct? Because the units are not matching. This is in semi inverse. Let's forget about the ohm because we are dealing with the concentration term only. So semi inverse is important here because volume term is there in the concentration, right? So we should convert the liter in semi because the liter term is nothing but 1 liter is equal to 1 decimeter cube. See? So we can convert the decimeter. So decimeter and centimeter are related. All are length units, right? So we have to convert the decimeter unit to centimeter. How? We know decimeter and after that centimeter is there. So 1 decimeter is equal to 10 centimeter. Fine. Now 1 liter equal to again 1 decimeter cube means 10 to the power 3 semi cube. Clear? So here if we write Y moles per liter, right? Per 1 liter it was there like that concentration. So let's not write now the lambda m. This is the only concentration C. Okay. Now Y moles into 1 liter, we can write 1 liter as 10 to the power cube semi cube. This 1000? Fine. So it is Y by 1000 moles centimeter to the power minus 3. Fine. This is the concentration. Now we have to put the concentration in the lambda m. Okay. So lambda m was kappa by cm, we know. So kappa value is X semi-inverse and ohm inverse. Okay, and now concentration we can write because the units are same. 1000 moles semi minus 3, sorry 3 minus 3, yes. Now it will be X by Y and 1000 will be go upside, right? Will be 1000 and unit will be, I'm writing here, ohm inverse, mole inverse and semi square, right? Right or wrong? Tell me. So in that portion where the unit of molar, yes, unit of molar conductance, okay, we have written that was the unit only, ohm inverse, mole inverse and semi square, right? So we got correct. We got correct actually here. So overall, if I remove these parts, so if I write now the lambda m, this will be now X by Y, 1000 into, let's say, X in by Y. So unit is ohm inverse, semi square and mole inverse, right? So these we got. So we can convert it like this way because Y is the concentration. So 1000 into kappa value. This is kappa value and this is the concentration. See, we can convert it. So my equation, this one was correct. Correct? Because I have taken that equation only. Just I have changed the units. So my advice is forget about these things. Okay, you can just remember that whenever concentration is in molarity, you can write the expression with that. Okay, but if you confused that this is right, this one is right or this one is right, then just remember this one because it is the only the actual formula. For only molarity case, the equation will be converted to that. Okay. Now, the same is actually valid for the normality also. When we are expressed in normality, that time equivalent conductance will be 1000 into kappa and concentration in normality. This is molarity. Fine. So if you can remember, please remember it. Otherwise, just remember this one and try to convert the units. Okay. Now relation between lambda equivalent and lambda molar. Okay. So we know if we take actually the equivalent weights. I have told you when I was teaching I was introducing the normality, right? So we know that this is what? Kappa by, this is molar concentration. This is actually number of moles per unit volume per liter, let's say. So it is the moles per liter. So mole we know, mole we can express in various way, but we have to compare between these two. So I am taking here the weight taken X by its molar weight by liter. Okay, so it will be now kappa. This is X by M. Okay, you can be confused with this. Okay, so it is X by M moles This is moles, right? Number of moles can be expressed like this way. So this can be now, so M can be upside and X is here. Okay. So it will be, again the unit will be mole inverse and liter inverse and here ohm inverse. Let's say semi and okay, liter, let's say semi square. So we have to add 1000 here. Fine, because it is let's say it is the case of molarity, because mole per liter we have taken now, so we have to multiply it with 1000. Fine. So lambda m, what we got, 1000 into kappa into m, which is the molar weight by x. Okay, so m is here molar weight. Fine. And x is the weight taken. Weight taken. Fine. This is true, right? This one. Okay. Now coming to this. So lambda equivalent, it will be same like this one, just the equivalence per liter, let's say, like normality. So it will be now converted into like same way, will be kappa into E, equivalent weight, not molar, and X, let's say same amount of we have taken. So X is taken and now we have to write E also, this is equivalent weight. Okay, so this is the one and this is number 2, equation number 2. And we have the I have previously also wrote that what the relation between equivalent weight and molar weight, it is m by z factor, right? So if we put here that value, because m is there na, we can cut it. So equivalent the expression of equivalent conductance will be 1000 into kappa into now m by z factor into x. This is 3, let's say. So now if we divide 1 with 3, what we get? Lambda m by lambda equivalent will be 1000 kappa kappa m, this will be cut down, and also x. So what we get actually 1 and this is 1 by z factor. This will live. Okay. Obviously it will be equal to z factor. Fine. So now we get the relation that lambda m is equal to z factor into lambda equivalent. Okay. So we have to have the idea about how we can calculate the z factor also. Okay. So how to calculate z factor? For let's say electrolytes. Electrolyte means which let's say NaCl, which are let's say this is actually they mean to say that strong electrolytes means some salts which in the solution, which components in the solution, they can change or they can dissociate into ions. Okay, so for electrolytes, Z factor equal to total number of positive or negative charge. Total number of positive and negative, no, this is or. We have to calculate total number of positive charge or the negative charge. Fine. Now example NaCl. How it can dissociate? NaCl, Na plus and Cl minus, right? So total number of positive charge is 1 and total number of negative charge is also 1. So if we calculate via the cation or anion, in both cases the answer will be say equal to 1, right? Let's say another example we have taken. CaCl2. So this can be dissociate with this Ca2 plus and 2Cl minus. So total number of positive charge is 2. Total number of negative charge is 2 into 1 equal to 2. So in both ways, Z will be equal to 2, Z factor. Let's say one example, another example I have taken, which is Fe2 SO4 OH. Okay. So we have to see the ions which we got after dissociation. Okay. This will be Fe3 plus and 3 SO4 2 minus. So total number of positive ion is, let's say, Z plus. Okay. Is 2 into 3, that is 6, and total number of negative charge will be also same. Just for your understanding purpose, I am writing that 3 into 2, which is 6. Fine. So Z will be equal to 6 here. Understood? Now for ions, let's say ions are given. For example, okay, Z factor will be charge on that ion. Let's say any ion, let's say sodium plus ion, Z will be 1. Fluoride ion, Z will be 1. SO4 2 minus ion, Z will be 2. Like that way. Okay. Let's say cobalt 3 plus ion, Z will be 3. Fine. Now you have understood how to calculate Z factor. Now you can have the relation between the delta lambda m and lambda q. How they are related, you can calculate that. Okay. Now coming to the question. This is a CSIR NET December 2017 question. If the specific conductance, what is specific conductance? Conductivity or this kappa of an electrolytic solution is 0.2 ohm inverse semi inverse. The cell constant is this one. The conductance of the solution is okay. So what we know? We know conductance equal to kappa into, okay, forget about that. What we know from that resistant formula, rho L by A, right? If you forget that also, the formula for conductance, okay, we can start with that also. Like that way I am solving, that you have forgotten that formula, okay. So 1 by, just take, I have taken inverse, 1 by rho and 1 by L by A. L by A value is given, see, and kappa value is also given. So this is kappa, this will be kappa into 1 by L by A, okay, and this is lambda. So lambda will be, what is the kappa now? 0.2 into 1 by cell constant value is 0.25, and both, see, both the units are same. That's why we don't have to convert it uh, into something else. Okay. So ohm inverse, what was that? Kappa value, ohm inverse, semi inverse, and in the below, that is semi inverse. So it will be cut out and it will be ohm inverse only. And we know the conductance unit is ohm inverse. Fine. So what will be the answer? Try and calculate. This will be 0.8. Okay. 3 will be the answer. 0.8. This same unit. What is the unit? Ohm inverse. Fine. Now coming to the same kind of question. See, again in the CSIR NET, this was I did not change it. I think this is June 2017. Okay. So this is also CSIR NET question. The specific conductance kappa value is given 0.176 ohm inverse, semi inverse, and cell constant L by A is 0.225 semi inverse. Again the nothing unit conversion is there. Okay. So conductance is, we know kappa into 1 by 0.225. Fine. So 0.176 divided by 0.225 will be what? 255 is there, right? 255. Sorry. So it will be 0.7, 0.69, right? This is not the answer. This will be the answer. Okay. Now coming to the a gate question. Okay. Here another one interesting concept is also needed. It was also you have read about. So the molar conductivity, what is given? Lambda of a weak acid is measured in a conductivity cell with cell constant. Okay, cell constant is given cell by A, zero point 0.4. Semi-inverse, don't forget about the units. So measured in a conductivity cell with is this. This is the molar conductivity. You can understand it by seeing the units also, right? Siemens or Simon, then is square and mole inverse. Fine. This is there. And the limiting molar conductivities of H plus and X plus. Why these things are given? Okay, I will tell you. So when we will read the uh, okay, when we will read the effect of dilution or how the when we change the concentration, how the lambda m value actually varies. That time we got that for the case of strong electrolytes, this that plot will be like this, because with dilution, this is the concentration and this is the lambda m. Let's say so with dilution, actually lambda m value increases. This is true for weak electrolyte case also, but we can't never for the case of weak electrophile, we can never find out that limiting lambda value, okay, which we can get from the strong electrophile, this one. But for the case of weak electrophile, that will be just a little bit parallel with the y-axis, okay. So we can never find that value. When the concentration is tends to 0, the lambda m value is called lambda m value is called the limiting molar conductivity. Okay, so we can find that in the case of strong electrophile. Okay, electrolyte. So here limiting molar conductivities of H plus and X minus is given. Fine. So it is said, this is actually Colora's law, and it is said that we can't find out from the graph the limiting molar density, molar conductivity of weak electrolytic solutions. Okay, but we can find that with a by taking the constituents ionic for these ions. I'm confusing. Okay, I'm sorry. So this is only the okay. The points I am writing. Okay. So for the case of weak electrolyte, there is no way, or from the graph, let's say from the graph, we can't find out the lambda m0 value because it is not cutting the y-axis. Okay. So what we can do, let's say this is weak electrolyte Hx. This will after dissociation it will form H plus and X plus, X minus. So if we know that the values of the let's say the values of the lambda m0 of H plus and X minus, okay, and we can add these two, we can find out the lambda m0 value of Hx. Okay, this will be equal to lambda m0 of H plus lambda m0 of X minus. This is the only thing. This is the Colora's law. Okay. So sometimes here the straightforward these values are given for H plus and X plus, but sometimes it is not given. It is given like that HA concentration for the HA lambda m value is given. This is strong electrolyte and AX. Let's say it is given for HA, okay, and Bx, and another value is also given, which is AB. Okay, so these all are strong electrolytes. And how can we, the lambda m0 values are given. And how can we find out from here the lambda m0 value of Hx? This one, this lambda m0 value of Hx, how we can get? This will be equal to, this will be nothing but lambda m0 of Hx. Because, okay, yeah, and lambda m0 of Bx minus lambda m0 of AB. How I can write that? Because it will be, if we think about their constituent ions, it will be lambda m0 plus H plus lambda m0 of A minus plus lambda m0 of B plus and lambda m0 of X minus minus lambda m0 of A plus, sorry, B plus, and this will be BA actually, BM. B plus minus lambda m0 of A minus. So this and this can be cut down, and this can be cut down. So what we get? Lambda m0 of H plus and lambda m0 of X minus, which will be equal to lambda m0 of Hx. Okay, these things you will I will be talking in another session. Just for now, please remember that for the case of weak electrolyte, if we can add the values of lambda m0 of constituent ions, we can get the lambda m0 of that, the value of lambda m0 for weak electrolyte, for that electrolyte. Okay, so that is only needed here. Okay, so now what is given? I will take this question again when I will be talking about the concentration effect on dilution effect on conductance. Okay, in the next uh, lecture itself. Okay, so now what we can get? This value is given, and the Hx and X minus values like lambda m0 values are given. So lambda m0 of Hx will be what? X is given 350, and for y is given this. This will be 0, 6, 7. This is the lambda m0 value. Okay. Now, what we need? Ignoring the activity coefficient. Okay. What we need? The pK of Hx. Hx is an acid, right? It can dissociate like this. H plus and A minus. Okay. So, how we can write? From the kinetics you know, na? So, if the initial concentration is A, it will be 0, 0. If after t time X amount of Hx is dissociated, this will be X and X, right? And if we take the, let's say K, the dissociation constant for acid, that will be X into X by A minus X, right? So X square by A minus X, that will be. Okay. So this X is actually written as the alpha X. Okay. This is actually written as alpha X. Alpha is the activity coefficient. Okay. Alpha X, alpha square X square, and it will be alpha X. Okay. If we ignore that alpha, it will be just a little bit confused. Okay. Yes, I have done correct actually. I've done it correct. Just a little bit of changes. Okay. So This is A and 0, 0. So after T time, this will be A minus alpha A, because alpha is the dissociation the rate of dissociation or the activity coefficient. So this is actually the rate, alpha into A. Alpha into A. So A is the initial concentration. So this will be multiplied. Okay, alpha A. This you have actually read in the 11th or 11th class. So Ka will be alpha square A square by A minus alpha A. Okay. So for the case of they are saying ignoring the activity coefficient. Okay. So activity coefficient, if we ignore that time, it will be Ka. Okay, activity coefficient. This is not activity coefficient. This is the dissociation. Some dissociation rate is there. Okay. Okay. So this is actually very much less. This is less than 1. So we can ignore that part. So we can write this as alpha square. This is actually alpha is the dissociation rate of dissociation. So alpha square will be, this is applicable for weak electrolyte only, and it is written that weak acid. Okay. So alpha square into A by this A square, and A it will be cut out and it will be alpha square A. So now what we get, Ka equal to alpha square A. Okay, fine. Now see, the concentration of H plus is this one. Okay, but we need only pK value. Okay, fine. So pK value, how we can get? So we have to have the idea about the alpha value. A value we know. A is, I have taken activity, but the activity is actually equal to lambda into C. This lambda is activity coefficient. They said that to ignore the activity coefficient. So lambda, if we ignore, or it will be equal to 1, then activity will be equal to concentration. And concentration is given here. Okay, this is a long question actually. So this will be what? Now I am writing here. So now the alpha, so A is A we know, right? So Ka is, it will be alpha square into concentration itself, because we have neglected the activity coefficient. This is activity coefficient, and alpha is the dissociation. Okay, dissociation some coefficient. Okay, so it will be, this is actually equal to the lambda m by lambda mc. That's why actually lambda m0 we have calculated here, and lambda m value is given here to calculate the alpha value, the dissociation. So it will be 64.4 by 766. Fine? This is fine, right? I will take that question after when I teach the effect of dilution and everything. Okay. So just now see this. Okay. So this will be equal to 64.4 by 760. It will be 0.084. Okay. Alpha value is this, and Ka will be now equal to 0.084 square into concentration is 0.01. Okay. So if we multiply this, we get the value 7.17 into 10 to the power minus 5. Okay. So if we take now pK is minus log of K, we all know, and if we put the value of K here, we can get the answer. Okay. The calculator is given in the GATE exam, so you can calculate the pK of the acid. Okay. So if you are confused, let me just summarize it to you. So here lambda m value is given, but lambda m 0 is not given, and we can't actually directly know about the lambda m 0 limiting molar conductance. We have to have the idea about the that constituents ions, that ions molar conductivity that is given. So if we add this, we can get the limiting molar conductivity of that particular weak acid. Fine. Why we need this? Because alpha, the dissociation coefficient of this weak acid will be the lambda m by lambda m 0. Okay. So if we do that, we get the value. Okay. Now they said that pK value is needed. So for acid dissociation, if the initial activity is A and this is 0 0 because T is 0, and if T equal to T, that time it will be the concentration of HX left will be A minus activity dissociation coefficient into A. In this rate actually the acid is dissociated. Okay, so this will be the, this is the rate, and if we multiply with the initial activity, it will be the amount of acid which is reacted. Okay, and this will be the amount of H plus form, which will be the amount of A plus form, and like that way if we write down the Ka formula and we neglect the alpha A, it will be very less, we get the alpha square A. Now they said that activity coefficient we have to neglect, and this activity is equal to activity coefficient into concentration. So we can convert the, we can write in the place of activity, we can write the concentration. Now we know the alpha value and C value. If we put that, we can get the Ka value, and Pk is nothing but minus log of K. Okay, so we can get the value of Pk. Understood? So this was a very lengthy question. So I hope you have understood this. So if you have any question, please write down below so that I can see and I can help you out. And in the next video, I will be talking about the conductance itself and the dilution effect on conductance. So this is very important, and theory part, from the theory, that theory also questions are asked. So stay tuned with me and see you in the next lecture. Okay. Thank you for listening.